So let's start our last talk for today, Ricardo Carrera. And it is the essentials in kReg and W. Go ahead.
Great, thank you. First of all, I'd like to thank Jim and Jim for organizing the conference. Jim, I'm sorry I wasn't able to make it out there once again to LSU. I promise you one of these conferences I'll definitely be able to head on out there. Thank you for setting up the remote talks. It's been very helpful, and it's been good to see the talks thus far. So hopefully you all will enjoy the last talk of the day. So I want to talk about the essentials in kReg and W. So basically, the goal is to provide an overview of essential morphisms and essential extension in Hall classes, both in kReg and W. I want to be able to give an overview of the similarities between the two concepts within the respective categories, and how those similarities allow you to develop a theory of Hall class in kReg. So the talk is going to be broken up into 4 parts. The first part is just preliminary background information. Then I'm going to go into essential morphisms and essential extensions in kReg and W. I'll go ahead and define Hall classes in kReg and W, and then give some results about how to go about identifying, generating, and working with Hall classes in kReg. And then at the end, I'll provide some examples and some applications. And then hopefully, if there's a little bit more time after that, I'll be able to talk about how this work is actually related to other categories of frames. Okay, so by now we all know what a frame is. It's, you've got a complete distributive lattice that satisfies the infinite distributivity property. We've gone over what it means for a frame to be compact. This here is the pseudo complement. Me, because my formal training is in L groups, I tend to call them polars. So I go P and F is a polar if P is equal to A perp. And I'm going to let PF be the set of all polars of F. I think it's also in the frame language, some of you might call it the Booleanization. So PF is a complete Boolean algebra in which infima agrees with those in F. And then the last concept that I don't think anyone's, the last concept that I don't think anyone's defined thus far is the well below. And so 2 elements, A and B, are set. A is said to be well below B if B sup A perp equals 1. And an element B in a frame is said to be regular, provided that B is equal to the join of all the elements that are well below it. And if every element in the frame is regular, then we say that the frame is it's a regular frame. In terms of morphisms, these particular types of morphisms and properties of morphisms will be of particular interest to us. So first of all, if you have a morphism from F to H, then phi star is going to denote its right adjoint. It's well known that the right adjoint preserves all existing infimum. If you have the map phi from F to H, it's said to be dense. If phi of A is equal to 0, implies that A is equal to 0. And phi is said to be star dense. If phi star of H is equal to 0, then H is equal to 0. The other maps that will be of particular use will be the concept of a skeletal map. So a map phi from F to H is said to be skeletal if whenever A per perp equals 1 in F, then phi of A per perp equals 1 in H. Or equivalently, you can think of this as a map that maps dense elements to dense elements. Okay. So it's well known, this is the typical characterization, one of the typical characterizations of a skeletal map. So if you have a map phi from F to H, it's skeletal, if and only if it satisfies this, that it induces a Boolean homomorphism from PF to PH, so that it makes this diagram here commute. And then the map is defined as one would expect down here, P of phi of A per perp is just phi of A per perp. As previously noted, we're going to be, for the most part, confined to kReg, the category of compact regular frames with frame homomorphisms. And W is going to denote the category of Archimedean L groups with designated weak unit and L homomorphisms that preserve the weak unit. So from W, this is really pretty much what I'm going to utilize. And so it's the counterpart of some of the concepts that we're looking at in terms of in frames. So for S and G, you're going to define S perp to be all the elements in G that are disjoint, if you want to think about it that way, that are disjoint to every S in S. Then S double perp is the polar generated by S. So just so that you know, a weak unit is a positive element whose perp is 0. So for example, if you take C of X, the rings of continuous functions is a prototypical W object. And there, in that particular object, the constant function 1 is usually what's denoted the weak unit, but you could take any element whose co-zero set is dense, and that would be another weak unit. All right, throughout P of G denotes the set of polars of G. And as is the case with frames, P of G forms a complete Boolean algebra. But in here, the infimum is basically just intersection. Okay, so this is the prototypical characterization of a one-to-one map that was due to Banaszewski. And so in kReg, phi is a one-to-one map if the following holds. Phi of A is equal to 0 implies that A is 0. So in other words, the map is dense. And then there's this other characterization, this other property that's equivalent. Phi of A is equal to 1 implies that A is 1. And so this is codense. And so if you have a map that satisfies any of these properties, then it's going to be harmonic in this category. All right, Banaszewski defines the concept of an essential extension in the category here. So you have H as an essential extension of F. If whenever you have a map F from H to M in kReg, and the composition is 1-to-1, then F happens to be 1-to-1. So just the prototypical definition. All right, so in kReg, the essential monics can be characterized in the following fashion. So phi is an essential extension if and only if phi is dense and star dense, if and only if phi is skeletal, and P of phi from P of F to P of H is a Boolean isomorphism. So let me just give you a little bit of the background. 1 implies 2. This is something that Banaszewski showed in that paper where he defined the absolute, which we're going to get to in a second. And 2 implies 3 was also proven for arbitrary frames by Hager and Martinez in 2007. What's different here is that typically 3 does not imply 2, okay? But it does in this particular category. And the reason that it actually works here, just to give you a summary, is because of the fact that the compact regular frames, right, they're generated so for example, if you take an element, it's the soup of the polars of an element that's well below it. And so using that in the skeletal feature allows you to get the other direction. All right, another thing that this category has that's very nice is the factorization properties of essential maps. So for example, if you have H is an extension of F and M is an extension of H, then M is an essential extension in F if and only if each of the factors happen to be an essential extension. In addition, one also has the following, that the essential maps are actually epimorphism with respect to essential maps. And so in this particular paper, one can get this result from the fact that in fact that essential maps are actually epi with respect to skeletal maps. That particular proof utilizes, it's more of a categorical approach. The one that Papi and I gave in a recent paper is one that really has nothing to do with it doesn't make use of the maximal essential extension, which I'm going to talk about, which this one does. This is purely intrinsic to these two frames, and you can just show it based on the properties of the skeletal feature of the maps and the representation of the frames with regards to their polars that I was alluding to. All right, so what does this have to do with W? Well, the way that this is related to W is as follows. In W, a lot of the results that we just saw, W has the same corresponding results. And so, for example, in W, the monics are one-to-one maps. And then you can define essential extension in the same fashion, right? If the composite is one-to-one, then F is one-to-one. And in W, you also have the feature that the essential morphisms can be characterized basically in the same way. So phi is an essential extension in W if these two conditions hold. The second condition says for every H greater than 0 in H, there exists a G greater than 0 in G and an N in N, for which G is less than or equal to N times H. And the third one says that phi is a complete L homomorphism, and that P of phi from P of G to B of H is a Boolean isomorphism. So in other words, the trace map of the polars, and by tracing being the intersection, the trace map of the polars of H onto the polars of G is actually 1-to-1. Okay. So the first thing to notice is if you look at condition 2, right? Condition 2 is really the W counterpart of the star density requirement for an essential extension in kReg. Right, the density part is the fact that it's 1-to-1 map, okay? But this condition gives you that star density requirement, okay? Also here, a complete L homomorphism, a W homomorphism is complete if it preserves all existing supremum, and I'm not really gonna get into it, but the completeness here is the counterpart of the skeletal feature in the other result. Okay, as it was the case in kReg, in W, you also have that the factorization of essential extensions is nice. And so, for example, if you've got these extensions here, then you have that M is essential over G if and only if each of the factors happen to be essential, okay? Likewise, the essential maps in W are epi with respect to essential maps. And so if you have an essential extension, then if you have any other two essential maps from H to M, that agree over G, then they actually have to be the same map. All right, so we've discussed some of the similarities between the essential morphisms in kReg and W, but there's another feature that both kReg and W share, which is going to be actually very beneficial for what we want to do. And that is the existence of a maximal essential extension. So Banaszewski showed that for every compact regular frame, there exists a strongly projectable compact regular frame E sub F and a 1-to-1 star dense frame map that goes from F to EF. And this is the way that the map is defined, such that whenever you have an essential extension of F, then it embeds into EF such that EF is equal to phi composed eta. Okay. So here's a couple of things. This embedding is going to, this eta is going to be unique over the base. And that follows from the property of the fact that the epis happen to be, that the essentials happen to be epi relative to essential maps and the factorization provision. And so, and that also plays an important role, as we will show in a little bit. So let me just go back. Strongly projectable, because I don't think I defined it anywhere, but strongly projectable just means that every polar is complemented. So if you take a polar P, then P sub P per equals 1, okay? The other thing is that the frame EF, which I didn't write here, but it's good to know because I'll probably refer to it this way, is what is called, it's essentially complete, which means it does not admit any proper essential extensions. All right, well, in W, the counterpart of that is Conrad's essential completion, okay? And what that says is basically for every W object G, there exists a strongly projectable, and this one means that every polar is a summand in the group. It's essentially complete, a W object, EG, and an essential map, EG from G to EG, such that whenever you have an essential extension, it embeds into the essential completion. And again, you also get this uniqueness provision, which is very useful. Right. So I'm going to go ahead and give you now the definition of a Hall class. And so a kReg Hall class is defined in the following fashion. So a class of kReg objects is said to be a Hall class if it's closed under isomorphic copies. Okay, and for every F, well, wait a second. For every F in kReg, there exists an H of F in H, such that H of F is an essential extension of F. And whenever you have any other essential extension over F, and H belongs to H, then there exists a map H of phi from H of F to H for which this composition holds. Okay. So I'm just gonna write boldface H, comma H to signify that H is a Hall class and that the little h is the Hall operator. And if you do H of F, comma H subscript F, then this is what's going to be called an H Hall of F. So in this definition, it's possible to have many H Halls, but you can show by using the this minimality provision and the epi feature of the essential maps that in fact, all the H halls are unique up to isomorphism over F. Okay, so in W, you can define the concept of a Hall class in exactly the same way. So just go ahead and replace kReg with W, and you'll have a definition of a Hall class in H. There are also other ways to define it, which turn out to be equivalent. But this, if you think about it, this is the one that's more categorical in nature. And so what do I mean by that? If you look at the way that this is written and you think about it for a little bit, you can see that an H Hall is nothing more than a reflective subcategory if you just restrict yourself to the category of kReg frames with essential maps. Okay, so you're basically looking at a reflective subcategory in that category. And so this is the one that has the most of a categorical, the most general flavor to it. Okay, so what's going to come work, what I'm going to talk about now is basically joint work that I did with Papia. And it's some of the recent stuff with regards to the Hall classes in kReg. All right, so as is the case in W, the existence of a maximum essential extension and the epimorphic properties of an essential map, and also the factorization properties of these essential maps, allow you to, get a representation theorem of an H Hall of F. And so what do I mean by that? It's basically this. So suppose that you have a Hall class, and this is in kReg. Suppose that you have a kReg Hall class, okay? Then for each F in kReg, there's going to exist a kReg subobject. I'm going to call it HF here of EF, for which the following equivalent conditions hold. Whenever you take any other H Hall of F, then remember that this gets mapped into the absolute. Well, the mapping that maps it into the absolute is going to actually take it to that unique object, okay? And then, of course, it's going to satisfy this composition requirement, okay? So that's one way to characterize the H Hall. The other condition is here. This object has basically the canonical embedding of F in EF as a subobject. Here this denotes inclusion, okay? And so if you take H of F, comma H of F here, where this little map here is the co-restriction of the canonical embedding to this, then in fact, this guy is also going to be another H Hall, okay? The third condition is that this object in EF belongs to the Hall class. It contains the base object. And whenever you have another kReg subobject of EF that happens to belong to the Hall class, then in fact, it must contain this one as an intermediate, okay? And so if you have any kReg subobject of EF that satisfies any one of these requirements, then in fact, it's going to be an H Hall. And because all of them get mapped to the same thing, it makes sense that you can call it that's in fact just the H Hall itself, okay? And so you can show that this is the unique object for which all these properties hold. Okay, so what does this have? How does this help? So basically, I kind of already alluded to this. In light of that previous theorem, if you're given a Hall class, it makes sense to talk about the H Hall of F within EF because they're all isomorphic to a unique object, any H Hall that you can think of, okay? But more importantly, what this tells you too is that if you want to generate a Hall class, then one way to do that would be if you could, for each kReg object, if you can go inside the absolute and generate or give a description, a concrete description of its H Hall, then you would be able to go ahead and produce a Hall class, okay? And in fact, in CA16, I use polar functions to basically generate various examples of Hall classes within the absolute of a compact regular frame. Okay, so let me just make a comment that this is typically what's done in W2. So for example, if you go into W, for everyone that's familiarized with the theory of Hall classes in W, this will make, it should be fairly natural that this is happening. If you want to, complete a particular object, what you do is you usually go into the essential completion and you adjoin the elements that you need or that you're looking for, right? And you do this transfinitely and you close it up until it produces the Hall that you're looking for. And so this is a prototypical approach that's usually applied. And the same thing will hold true here in kReg, okay? Now, here's the thing though. I mean, if you just look at the definition that was given for a Hall class, that was, it was more of a categorical one, right? And it was a categorical one. And so it's not clear that if someone just happens to have a Hall class, that you can always construct or get a concrete description of the H Hall within EF. And so the question becomes then, all right, if I can't do that, is there any way for me to identify that if I have a class of kReg objects, that in fact it's still a Hall class? And what sort of information can I get from it? And so here are going to be some sort of construction-free approaches to determine when a class of kReg objects is a Hall class. All right, so the first one says the following. Let H be a class of kReg subobjects that is closed under isomorphic copies. H is a Hall class if and only if, whenever you take an essentially complete kReg object, and B is a collection of kReg subobjects of E, for which B belong to the Hall, and if you intersect them, and then this row here is a regular co-reflection, you take a row of it, if that's essential in E, then in fact, this belongs to the Hall class, okay? And so you can show that this is the case, and the way you prove this is by using that representation theorem of a Hall. And so what you do is you just go ahead and you look at what's happening within the absolute. And I guess what I really didn't say, because I didn't, I'll just briefly touch upon it. If you've got a Hall class, then all the extensions by members of that Hall class over F get mirrored within the absolute. And so to understand how these things are related, it suffices to look at what's happening with the subobjects within the absolute that contain the embedding, the canonical embedding of F and E of F by subobjects that belong to the Hall class and contain the canonical embedding of F and E of F. And so this is really what that's banking on. And so you could just go ahead and show that that's the case. You can do it that way, and that's one way of proving it. Okay. All right, so the previous theorem is the kReg counterpart of the following result from Martinez and Hager, which says the following. If you have H is a Hall class of W subobject, so let H be a class of W subobjects that is closed under isomorphic copies. So again, this is going to be a Hall class if and only if, whenever E is an essentially complete W object, and B is a collection of W subobjects of E, for which B is contained in a Hall class, and the intersection of B is essential in E, then this intersection happens to be back in the Hall class. And so this here is basically just that result, but for compact regular frames. So theorem 12 is the frame counterpart of this result here. All right, so theorem 12 provides a technique by which to generate kReg Hall classes. So we're going to call a property P of a compact regular frame to be a Hall property, provided that it satisfies the following two conditions. Whenever you have F, it's isomorphic to L, and F satisfies P, then L must satisfy P. And I'm going to say that P is essentially intersective, which basically means that if you take an essentially complete object and you take a collection of kReg subobjects of E such that B belongs to B, satisfies B, then if you look at the intersection and you apply the regular co-reflection, and that's essential in E, then that also has to satisfy P. So in other words, that it meets that requirement that we needed to for theorem 12. Okay. All right. So if you have that, then clearly you're going to get that for a Hall property P. If you define H to be all the F and K regs such that F satisfies P, then this is going to be a Hall class. Okay. You also get by by basically using theorem 12 again, that if you have a collection of Hall classes in kReg, then if you intersect them, okay, then that's going to also produce another Hall class. Okay. So this here, theorem 16 is, they have an equivalent result in W for it, the same thing. This phrasing here of a Hall property, so typically, I haven't seen it, the definition of a Hall class formulated that way in W, but there's no reason why it couldn't. I mean, you could very easily do it. This usually seems a little bit more like what's done in topology with regards to covers, and I'm going to talk a little bit about that in a second. Okay, so up to now, we've seen some techniques for generating and identifying Hall classes. And by the way, all of those techniques and all that stuff that we were looking at, none of that required the axiom of choice. Okay, but now we want to go ahead and provide at least a couple of devices, a couple of techniques for determining when a class of objects is not a Hall class. Okay, and so the motivation for these results, as we will see in a second, comes from topology. Okay, well, with the exception of this one. Sorry. So this one, and this one's kind of obvious and straightforward. So the first one is that if you take any Hall class, that it must contain all the essentially complete kReg objects. That's because the Hall class is closed under isomorphic copies, and an object that is essentially complete must be isomorphic to whatever H Hall you generate. Okay, so because of that, you obviously you get this is really obvious. If H is a class of kReg objects and the essentially complete objects are not contained in H, then H is not a Hall class. For the second approach, we're gonna have to use maximal elements. Okay, so we're gonna have to assume the axiom of choice. So let's really quick recall. An element m that less than 1 in F is maximal, means that if you have A greater than or equal to m but less than or equal to 1, then either A is equal to m or m is equal, wait, that's a typo. Either A is equal to m or A is equal to 1. All right. For F in kReg, max F denotes the collection of maximal elements of F. And we're also going to use basically this concept here from Banaszewski. For A and F, we're going to define M sub A to be all the X in F such that X is less than or equal to A or X sub A is equal to 1. So M of A is basically the frame counterpart of the quotient space construction when you take a closed set and you identify it to a point. And so Banaszewski showed that if this M sub A is compact and regular whenever F is compact and regular. Okay. All right, so this is really not too difficult. I mean, you can literally just show this. You can show that if you have a map phi from F to L in kReg, then phi star maps maximal elements to maximal elements. Okay. So then using this result, along with the properties of essential morphisms in kReg, one can prove the following. If you have phi from F to L in kReg and K is a non-empty proper subset of max L, it could be empty. If it's empty, it's the trivial case, but I just wrote non-empty. If K is non-empty proper subset of max L, such that for every A and B in K, phi star of A is equal to phi star of B. Okay, so suppose you have this set meets these requirements. If you go ahead and you take the infimum of it, let's call it little k, and let M sub K be defined as above, then phi is going to factor this way. Okay, where phi star is the co-restriction of phi to this subframe of L. And moreover, you get that phi is essential if and only if phi star and I are essential. Okay, and so one can check that this is the case using factorization properties of the maps in kReg, and then the definition of M sub k. And the part about the essentialness with regards to the factorization, well, that follows from the fact that the essential maps in kReg have that factorization property. Okay. All right. So what does this mean? So this is, if you think about it, this is basically an extension of the result that you get if you look at the category of compact Hausdorff spaces with continuous maps. So in that category, there's a theory of covers. And so the theory of covers, if you remember, if the axiom of choice kReg is just the dual of comp. So you could think of a cover as the dual of a Hall class of what we're defining here. And so what this is saying for the people that are familiarized with covers is the following. If you take a cover of a compact Hausdorff space, and then if you take the covering map and you take 2 points, right, that collapse to the same point or that are not distinguished by the covering map, if you identify those 2 points and look at the quotient that you get, then that's going to produce another cover. And in essence, this is what this is. This is the frame, the kReg counterpart of that result. All right, so using the previous theorem along with the properties of maximal elements in kReg, then you can show, this is another little technical lemma that in fact, if you have a map phi from F to L in kReg, and you have phi star from max L to max F is not 1-to-1, then the image of phi of F is basically the intersection of all these subframes in L, okay? All right, and so this you can do using the representation of elements via the maximal elements in the frame, and you can go ahead and show it, and you get this. Okay, so once you have all of this, you can put it together to basically get this result. Let H be a class of kReg objects that is characterized by satisfying some property P. If there exists an F in kReg for which F does not belong to H, but if you look at basically all these subframes inside the absolute, okay, if this is a non-empty set and it's contained in H, okay, then H cannot be a kReg Hall class. Why not? Because you see, if you intersect over all these guys, right, according to this theorem, that should be basically what the canonical embedding of F in E of F is. But if F is not in the Hall class, right, then this cannot be that intersection cannot be in the Hall class. And so it doesn't satisfy the theorem 12 provision. And so therefore you can't have a Hall class. Okay. And so what this is, and what this is basically is this is the counterpart of a device that's done in topology. Tony, Anthony Hager did this. All right, and it's basically let me see, it should be written here. Yeah, it's a corollary. It's basically the kReg counterpart of corollary 9.2. And so all this preliminary work is to be able to get this to work at the end. Okay. All right, so at least this gives you one technique for identifying when you have a class of kReg objects and that it's not a Hall class. All right, so let me go ahead, and I wanted to, how much time do I have left?
Well, you're over time a little bit, but you're the last talk, so it's not that bad.
I'll be done like in 5 minutes, 10 minutes, five minutes, okay. So I just want to give a couple of examples here. Okay, so DR is the frame of reals. You're going to have an element in F is a cozero element, means that there's a frame homomorphism from D of R to F such that H of R minus 0 is equal to A. And cos F is going to denote the cozero elements of F. Throughout, alpha denotes a regular uncountable cardinal of infinity. Infinity means no constraints. A lot of this that I'm going to define here holds in a broader context. And some of it does not require the cardinal to be regular. But for simplicity, we're just going to assume all of that. Okay. And so the first thing here, A and F is an alpha cozero element if there exists an S in cos F such that its cardinality is less than alpha and A is equal to the sup of F. F is alpha disconnected if whenever A is an alpha cozero element, then A perp sup A perp equals 1. If you let alpha be infinity, then this is basically extremely disconnected. And if you let alpha be omega 1, then you get what's usually called, basically disconnected. An alpha cozero element A and F is alpha complemented, means that there exists another alpha cozero element B and F, for which A and B is equal to 0, and A sub P perp equals 1. A frame F is alpha clause if whenever A is alpha complemented, alpha cozero element, then A perp sup A perp equals 1. I should mention that all of these concepts, these two have their counterpart in topology, and they're they've been well studied. So there's a lot of results pertaining to these things. So this is something that may be a little bit different. A and F is what we call an almost alpha cozero element. If there exists an alpha cozero element C, for which C is less than A, but A perp equals F, A perp equals C perp. And so we're going to say F is almost alpha disconnected. If whenever A is an almost alpha cozero element, then A perp sup A perp equals 1. And the last example here is I'm going to say A and F is an alpha CC element. If whenever S is a subset of F, which is pairwise disjoint, which means that if I take two distinct elements in here and I inf them, I get 0. And for which S is less than or equal to A for every S in S, then the cardinality of S is in fact less than alpha. Okay. And so we're going to say F is alpha CC projectable. If whenever A is an alpha CC element, then A perp sup A perp equals 1. Okay. So keeping that in mind, there's a connection between all of these concepts. And so for here, alpha greater than or equal to omega 1 less than or equal to alpha, you're going to have alpha disconnectivity implies alpha CC projectability. Alpha disconnectivity implies alpha clause. Alpha disconnected implies almost alpha disconnected. And every single guy implies omega CC disconnected. And omega CC disconnected is basically just a finite pairwise disjoint. If you ever have a pairwise disjoint subset that's less than or equal to A, then in fact its cardinality is finite. And so in fact, all the compact regular, trivially every compact regular frame is omega CC disconnected. And one can show that. Okay, so so by using the skeletal and the factorization properties of essential maps, one is able to prove the following: that each of the properties in the above diagrams are a Hall property. And so as a result, you get that if you look at the class of all kReg frames that are defined by any one of these properties, then in fact they're all examples of Hall classes. All right, so the last thing is I wanted to give an example of non-Hall class. So, when Papi and I were working on this, we were really trying to look for a lot of examples. And so we kept up thinking with things, and we were always excited about, oh, I think we got a new Hall class. Yeah, but it didn't always pan out. Some we couldn't show, and then others we realized that wasn't the case once we were able to develop more machinery. And so here's an example. So take an element A and an element A and F. I'm going to say it's connected. If whenever you take B and C is greater than 0, and A is equal to B sub C, then their inf is greater than 0. So F is connectedly disconnected. If whenever A is connected element, then A perp sup A perp equals 1. Well, the class of connectedly disconnected kReg frames is not a Hall class. And basically to do this, what you go in there, you can show that, in fact, if you go into the absolute and you look at that M sub M N's that I told you, those constructions, that all of those, in fact, will be connectedly disconnected. But in other words, so let me go back. You can show that this doesn't hold for that class. Okay, so basically this happens. So you apply this theorem, and so you get that. All right, so I guess maybe I'll stop here. Okay. Any questions? Hold on, let me see if I can put this. How do I fix this?
I'll try to point the camera at the audience. Perhaps you will be able to see who you're talking to. So are there any questions? All right, well, let's thank Ricardo again.
Right, thank you so much. And really quick, happy Mother's Day to all the moms on the audience and also to all the wives.